Bien, disculpo a nuestro presidente actual, Ennio Pacini, de Brasil, que se incorporará enseguida, pero en mi rol de presidente honorario, pues puedo dar comienzo a este webinario de hoy, y si se incorpora Ennio, pues él seguirá presentando. Es para mí un gran placer estar aquí hoy. Les van a presentar a un extraordinario investigador que además tiene una cultura investigadora muy, muy amplia. Pero mi papel aquí es presentarles y comentarles brevemente de Alcompat. Alcompat Internacional es una organización que dentro del ámbito de la rehabilitación y la recuperación y protección de las estructuras trabaja a nivel iberoamericano, y tenemos tanto estos webinarios como los congresos COMPAT y como otras actividades, porque somos una federación en donde en cada país, en más de 14 países latinoamericanos, hay una asociación Alcompat nacional. Es un foro de intercambio de ideas, de innovación y de inquietudes. Y con ello ya dejo paso a Julio César, que les hablará de cómo son estos webinarios. Muchas gracias por asistir a esta sesión.
Hola, hola a todos, muy buenos días. Gracias por estar aquí. Bien, el día de hoy vamos a cerrar con broche de oro los senior webinar que bien hemos organizado en conjunto con el doctor Pedro y Alcompa. La verdad es que es un gusto que nos acompañen el día de hoy y también pues contentos de que nos acompañe Konstantin. Konstantin, gracias por tu tiempo, por tu presentación. Entonces, vamos a dar paso a la presentación y esperemos que les guste y todo este esfuerzo que estamos generando para ustedes. Gracias. Gracias, doctora Carmen. Adelante, doctor Pedro.
Gracias Julio. Muchas gracias Carmen. Bueno, Costa, lo han dicho Carmen y Julio, es un gran privilegio, un honor tenerte aquí con nosotros y al público. Quisiera decirles, bueno, Carmen, Costa y yo nos conocemos hace muchísimos años y nos da muchísimo placer que él pueda compartir con nosotros su investigación, donde él es uno de los referentes a nivel internacional. Eh, Costa nos va a presentar hoy una, un seminario que tiene que ver sobre, y lo voy a decir en inglés, Hot Topics in Research and Development of Sustainable Construction Materials. Y quisiera decir algo acerca del currículum de Costa, ¿verdad? Y también voy a leérselos en inglés porque hay algunas cosas que es un poco complejo traducirlas al español, más fácil decir en inglés. Costa Kovler is head of the Department Building Materials Performance and Technology at the National Building Research Institute. Yeah. He is co-leader at the Research Center Sustainable World at Guangdong Technion. He was born in 1957 in Moscow, and he is an Israeli citizen since 1990. His PhD in structural engineering from Moscow State University of Civil Engineering, 1986. He works at the Technion since 1991. And his research interests are high performance building materials, non-destructive testing, durability, shrinkage, and clip of concrete, as well as many other materials and characteristics. He has been member of the editorial board of 2 international journals, Materials and Structures, and Cement and Concrete Composites. He is fellow and honorary member of RILEM, member of American Concrete Institute and European North Association. He has organized several RILEM conferences. He is active member of several European concerted research actions. And he has been involved also in the development of standards, European standards, and from many other parts of the world. It is one important thing. He has been organizer and teacher in several RILEM PhD courses in several parts of the world: Australia, China, Denmark, Mexico, Northern Macedonia, Russia, Slovakia, Israel. And I have to tell you that Costa is gonna be with us next year in Monterrey in November with one of these very special courses, together with other specialists from around the world. Costa has chaired several expert committees in the Israeli Institute of Standards, and he's national representative in the Technical Committee of International Standardization Organization. In the working group radiation measurements. Costa has been reviewer and is reviewer of technical papers and research projects for more than 60 international peer-reviewed journals and research foundations. And has authored more than 100 peer-reviewed papers in international journals and more than 80 papers in proceedings of international conference, as well as more than 30 books and book chapters. He has authored 6 patents and patent applications. Combines teaching and research activities with consulting for the construction industry and government ministries. Costa is official consultant of the Israeli Port Authority, of concrete technology for marine structures and durability. And of course, there are many other important things in the curriculum vitae from Costa. Costa, it's a very big honor to us to have you here. In this senior webinar. Thanks a lot, and go ahead, please.
Thank you very much, Pedro. for your introduction. Thank you very much, Carmen, for your introduction and leading this webinar, and Julia and all the other people, including Anna, which is interpreting the lecture. I would like to thank all of you for inviting me. And first of all, Pedro, who's my old friend and colleague. And it's really my honor and pleasure to be with you and share with you by some thoughts, mainly for the future, because my presentation today is going to be, how to explain you, a little bit philosophical and introductive. I have prepared some more detailed presentation, but not for today. Maybe, as we discussed with Pedro a few minutes ago, there will be room for presenting it in the next year. And this framework, or maybe in some other framework for Mexican and for other Latin American friends and colleagues. So let me share my screen. Can I do it, Pedro? It's a time. Sharing the screen. Just a moment. Sharing the screen. Okay. This is not what I want to show you. Just a moment. I need to going. Okay, great. I found it. So usually I open too many windows. It's a little bit tricky to switch from one to another. So today I'm going to discuss some hot topics in research and development of sustainable construction materials. So the keyword is sustainability, sustainable materials, which is a very wide term. It covers many aspects related to technology and environmental sciences and applications. So I selected only a few topics, but let me introduce the place I'm working in. I am located in Haifa, which is a northern sea gate to Israel. This is a nice view on the Haifa Bay, which is Eastern Mediterranean side. And I'm representing National Building Research Institute, which is a joint venture between the university, which is a Technion. I'm working at the Faculty of Civil and Environmental Engineering, and the Ministry of Construction and Housing. And we have 4 different departments in the institute. I'm heading one of them. If you can see my mouse moving, so this is called Building Materials Performance and Technology. We have different labs. We have different research facilities, and we have some interesting projects I would like to touch a little bit today. So the outline is here. I will start with motivation. Then I will speak about 3 main dilemmas, challenging dilemmas, how I call them, which are related to sustainability of construction materials from the viewpoints of customers, manufacturers, and the society. First dilemma is natural versus artificial stone materials. Maybe this sounds a little bit strange, because most of my career, most of my papers I published in the literature are related to cementitious and concrete materials, which is artificial stone materials. And only a few are related to natural stone. So this is interesting to compare different pros and cons of these 2 groups of materials. Then I'm switching to another topic. I was active a few years ago, gypsum versus Portland cement materials. As we know, gypsum and Portland cement are antagonistic materials. They're fighting each other. And the problem is, and challenge is to how to find a peace between 2 of them. And then finally, I would like to speak about so-called low contaminant materials, including those containing industrial residues. And the second part of my presentation, which is detailed one, will not be presented today, but perhaps with Pedro's help, we will find a way for finding a slot in the next year, if there will be an interest. So motivation. As we know, construction does not only consume about 40% of materials produced in the world at about 1/3 of the energy, but also pollutes the environment. Second bullet is extraction of construction materials, including sand, gravel, clay, limestone, natural stone, which causes noise, vibrations, and air pollution. So how we can manage all these unpleasant influences on the environment? And of course, we cannot forget about transformation of land into built-up area. So, unfortunately, because we consume huge quantities of exhaustible resources, and because industrial production increases dramatically, let's say for the last century, more than by 50 times, and 80% of this growth happened in the second half of the 20th century. Huge consumption of natural resources doubles the production of raw materials every 15 years. And very unfortunately, only 5% of natural resources turns to end products. And the rest goes simply to a waste, often ecologically harmful and unsafe. So this is very challenging topic, not only for our generation, but this is a challenge for our kids and grandkids, for the next generations. So, and then I would like to discuss shortly why recycling is not so easy. Let's decide pros and cons of recycling. Again, I spoke about pollution, transformation of the land. What would be the solution? Like Professor Mehta mentioned more than 10 years ago, let's consume less concrete, because concrete is still the most popular building material. It's consumed in large quantities. After the water, this is the second consumable in the world. Let's consume less cement, and let's consume less clinker, and let's discuss and develop alternative materials and technologies. And of course, let's recycle. This is what Professor Mehta said. But the question is why it's not so easy. And the first dilemma I would like to start to discuss, natural versus artificial stone. Natural stone is used in the construction industry mainly as fractionated materials, as aggregates for concrete, both dense and porous aggregates, as mineral fillers. It's used for geopolymers, but again, it's fractionated material. It's powder or granular material. It's used as mineral pigments. It's used for thermal insulation, abrasive materials. So we are speaking mainly about quarry stone. And we are speaking about raw materials for manufacturing different kinds of building materials like cement, gypsum, lime, and other mineral building materials. Let's speak about natural artificial materials. This is another group, which is a kind of intermediate or overlapped materials, organosilicates, basalt fibers, foamed and liquid glass, basaltoplastics, expanded products like perlite, different kinds of adsorbents, mineral binders, and of course concrete, ordinary concrete, aerated concrete products, gas silicate and pressed powder products, etc., ceramics and fireproof products, and so on. And finally, I come to natural stone products, which are called sometimes dimension stone. You can see many different examples of dimension stone products. they're used for finished products. Let's say artificial stone tiles, paving stones, prefabricated panels, architectural details, interesting things to produce like benches and other interesting and important architectural details, vazons, interior details, sandwich panels, and many, many other things. So, but natural stone, like artificial stone, starts with rock extraction. And then I would like to discuss coercive or destructive versus non-coercive or non-destructive methods of extraction. Rock extraction methods. So first of all, destructive, which are dominating methods of rock extraction while rock is disintegrated in volume. And unfortunately, both extracted material and surrounding rock massive are damaged. So we are speaking about how to define them. It's sometimes the people say it's a barbaric technology. It's a blasting and impact. So it's really coercive, destructive technologies which influence a lot the environment. Then we have so-called partly coercive or partly destructive. Well, rock is disintegrated in a certain volume, but surrounding rock massive undamaged. And as an example, we can mention TBM or tunnel boring machines. When the extracted material is, let's say, fractionated material, aggregates, but the massive surrounding the tunnel is left undamaged. And non-coercive or non-destructive, while by both extracted rock and surrounding rock massive undamaged. So we can call it delicate rock extraction, which is used in dimension stone sector. Most of the technologies for dimension stone production is based on cutting and splitting stone. Let's start discussing drill and blast. I know that in Mexico and many other countries, also in Israel, in United States, in China, in India, and many countries, drill and blast is a dominating technology for extraction of rock. So I don't want to go into detail. So you can see that first of all, we need to insert the explosive, and then we need to blast. We need to drill first of all. We need to strengthen the roof, which is extremely important because the surrounding massive is damaged. And then, by the way, we need to invest money, and it's time-consuming technology to strengthen the envelope by shotcreting or by inserting the precast elements made of reinforced concrete. So it's not easy, but we have to do it. Depends on the rock, of course. And then we need to extract the dust, which is formed during the drill and blast treatment. And we need to extract all the material fractionated from the quarry outside. Okay, then mentioning shortly popular techniques in construction earth excavation works. So we are speaking about power and energy consuming machines, bulldozer, tractors, different Caterpillar is very famous company producing these machines. They consume a lot of energy, fuel. So this is something we need to take into account when we speak about sustainability. Caterpillar, many of you, I believe, are familiar with quarry and aggregate systems. You can see very powerful trucks and excavators and equipment for aggregates operations in quarries. And then a few words about TBM, which is like I mentioned, partially coercive. So this is a typical example of TBM. It's like a train. It's a real train. When we speak about Gotthard Tunnel connecting Italy and Switzerland, it's more than 40 kilometers length. When it was produced, it took a time, and during this project, 4 different TBMs, huge TBMs, worked at the same time in this Gotthard tunnels. Another example, which is very famous, is La Manche Tunnel, connecting Great Britain and France. Also, underground tunnel, which was made by these techniques. Then let's speak about non-coercive or non-destructive methods. These methods are based on cutting and splitting. And you can see a lot of interesting and very nice finished products, paving stones, wall materials, wall products, blocks, bricks, nicely decorated architectural things, retaining walls, many, many interesting things. Then masonry blocks. Also, it's dimension stone. It's very old photograph taken from one of the open quarry in Italy, or maybe not in Italy, it's in Malta. Malta has a huge deposits of very good limestone and very famous in dimension stone production. So then we can build our walls not only from concrete, but also from masonry blocks, which was very popular method of historical construction. Let's remind the time of appearing concrete. When do you think the massive concrete construction started in the world? Perhaps it started after the Second World War in Europe and many other countries, but mainly Europe, because half Europe was completely destroyed during the Second World War. So then concrete, I'm not speaking about Bauhaus and some other interesting examples. I'm not speaking about Roman concrete, which is a very nice example, but I'm speaking about massive concrete construction. So, and Carmen perhaps she knows better than many of us what is the durability of typical concrete structures. Usually, following the Eurocode, we speak about 50 years as a minimum. Let's say it's a targeted value, minimum or targeted value of 50 years of service life. But where and when these 50 years are? So after the Second World War, much more than 50 years passed. So then we need to speak more about recycling, about upgrading the structures, about demolishing. So this is a real challenge for the next generations. Less speaking about new construction and more speaking about new technologies, green technologies, recycling, sustainable technologies, power, not power consuming technologies, and not material consuming technologies. And this is perfect example. Saws, different kinds of saws and discs. They're very popular. You can see some examples of saws and discs. And of course, we cannot forget about Italy. Italy is a real world center of stone technologies, which are also used widely in many other countries, in Turkey, in Spain, I believe also in Mexico they're popular, but not so popular like aggregate production for concrete. Then you can see the photo when I had black hair. It was done when I visited the northern Italy, which is very rich by excellent examples of natural stone. This is a dolomite stone, and this is Carrara. Carrara, this photo, by the way, was made in 2001. And this is another technique which is based on laser and plasma jet. So we have different technologies. By the way, when I visited northern Italy, I found many interesting examples of so-called all-round technologies, because when you extract big blocks, big massive of stone, very good stone for the cutting and splitting, then you have, of course, some kind of waste. But this waste is not bad to utilize as a sand, as aggregate for concrete. And also, if this is a good limestone, why not to use it for production of cement? So this area is rich by different examples of enterprises producing different kinds of products. So in principle, we have to think about so-called zero waste. But zero waste is a kind of fiction. But we need to minimize the waste. And all the waste, or almost all the waste, should be utilized somehow. And this is a perfect example of what I saw in the northern Italy. And then this was done. It was a picture I made in Italy also, open quarry producing dimension stone. You do not see these power-consuming techniques. What you can see, for example, this is very popular in the last, let's say, 40 years. It's a diamond wire machines. Diamond wire. You can see the machine, which is like a robot. You don't need to operate this machine with a labor. So it can proceed automatically. It doesn't consume energy. It's about maybe 18 or maximum 20 power horses power. It's nothing. So you are drilling the hole. You can drill the hole through the mountain 2, 3, 4 kilometers length. And then you're drilling another hole. And then there is an interesting technique of connecting the holes with this very interesting techniques. And then you are just inserting the diamond wire. You can see it here. And then, but this diamond wire is a kind of high tech, which is adapting itself for developing in different kinds of rock, both hard rock and soft rock, because geology is a kind of unknown. So we don't know exactly what is expecting for us, what kind of rock. So this is very interesting and very promising technology, which was developed in Italy, let's say more than 50 years ago. And this is a plant, but this plant is located, look at this plant, producing big blocks, and then they are cut by different slabs, and these slabs can be further cut in tiles. Or this is a splitting technology. So this plant is located in the quarry just to minimize the transportation expenses, and the closure to the raw material is extremely important from economical calculations, and also energy and fuel consumption. Unfortunately, in many countries, and I'm criticizing what we have in Israel, in our small country, we have huge production, annual production of concrete. We are producing crushed stone for aggregates, both coarse and fine, maybe 3 times more than Americans produce and Europeans produce. But you can see how small, how limited is the part of dimension stone, because these technologies are almost not known in Israel, and this is very pity. In comparison to our situation, Italy is very famous by producing dimension stone. Of course, they produce a lot of aggregates, crushed stone, but much less than we producing in Israel. So this is what we have in Israel. I'm criticizing again our local technology. So most of the technologies for producing dimension stone, as you can see, labor consuming. So they're based on drilling and then splitting big blocks. And then you can see what we have. This is a handwork, a lot of handwork, manual work, which is not what we can proud of it. And then this is my colleague in one of the quarries in the northern Israel. You can see a lot of signs of drilling, drill by drill by drill by drill. It's a lot of energy is spent only for drilling. And then they're splitting these big blocks. This is outdated technology. We need to fight with this outdated technology and introduce as much as possible the high-tech technology based on splitting and sewing. You can see hydraulic hammers. They are very popular for rock production in Israel and also in other countries. And look at the finished product. It's a cut stone. You can cut everything now. It's a real high-tech technology. You can produce very sophisticated geometry, very sophisticated shape of the elements. You can see this shape and this shape and this shape. So it's a sky the limit. You can see some pictures. It was just 4 years ago. I was visiting one of the underground quarries in Carrara in Italy. And these are also the quarries in Carrara, underground quarries. And then you extract very finely, very delicately by cutting the blocks underground. You are not exploding the underground, because explosion in underground is very provocative. It makes problems for the next generation, because what we have, for example, here, Israel is very rich by sedimentary rock, like dolomite, limestone, and some others. But this sedimentary rock is simply a miracle. It protects the aquifer, the groundwater, from pollution, because if you explode underground, then you provoke cracking, and through these cracks, the polluted water, and maybe you heard about the pollution coming from the industrial zones, because many industrial plants are polluting. We have a lot of pollution coming in the form of SO2 gases and other acidic pollution. This pollution penetrates into the aquifer. So, and then salinity and the quality of groundwater is getting worse and worse and worse every year. So this is a problem for the next generations. Let's speak about the canceling or forbidding in the next years all these barbaric technologies of producing aggregates by explosive techniques, which are considered as cheapest techniques in rock construction underground. Open quarries are also a problem, because you have so-called wounds. If you don't want to see these wounds on the surface of the earth, and you don't want to see the craters like in the moon in a few years, in the countries like Israel, which is a small country, and we don't have enough land, then there is a problem also for open quarries. I need to repeat about the noise and vibrations, especially near the populated areas, near the cities. And then look at the techniques for producing dimension stone. So this is a plasma. As you could see, this is different instruments, popular. You can see some more details, advanced stone products, sandwich panels. You can see the layer of natural stone as external layer, which is very nice. Architects are very excited to see this interior and exterior. But by the way, there is no problem in the modern technology to produce a few millimeters, 1 millimeter, even less than 1 millimeter thickness of this coating very accurately, very delicately, and then to coat your products. This is a very advanced flow materials. You see, so all this communications should be hidden from us. And then you just put these large panels, large tiles, and you can make a repair if you need by opening this hole and then repairing the communications, the electricity, the water pipeline, underwater, underfloor heating if you need. So this is very important and very nice to know. This technology is very important for producing advanced stone products like architectural elements, decorative floors, and so on. So again, to repeat very briefly, environmental damage from coercive methods, noise, vibrations, artificial earthquakes, by the way, dust, air, and water pollution, visual impact to biodiversity due to the land conversion, surface water regimes altered by blasting, cracking in sedimentary rock above the aquifer. I just mentioned it a few minutes ago. What about non-coercive methods? They're free from deleterious environmental effects, no damage to the surrounding rock. New anti-nose and anti-resonance circular blades are introduced now in the industry. Consumption by the way of water. Of course, if you saw the wire, diamond wire, or another instrument, we need to cool this instrument by water. But look, the moisture, natural moisture in rock massive is not zero. The consumption of water in stone cutting operations for cooling can be significantly reduced, maybe even excluded by using the internal moisture of the rock and water recycled in factories. What do we have now? Unfortunately, the goals can be sometimes contradicting. On one hand, we need to speak about construction of engineering structures. Let's take an example as a tunnel. For making tunnel, we need to make it as fast as quick as possible. And of course, blasting, drill and blast method is very cheap and very fast. But again, don't forget about strengthening the envelope because it takes time, it consumes the time, and strengthening elements like reinforced concrete envelope. And then construction materials industry. Construction materials industry has another, let's say, priorities. Sometimes the real construction projects are, let's say, contradicting the construction materials priorities. For example, in Haifa, approximately 20 years ago, we have a new tunnel. It's called Carmel Tunnel, which is 5 kilometers length, which was done by drill and blast. But I suggested to the design company to consider using this aggregates, which is extracted material, because during this extraction, a lot of fractionated material is produced, and to produce aggregates for concrete, for example. But first of all, to use TBM, tunnel boring machines, which is not a problem to order even secondhand. But the problem is designer is very carefully calculating the diameter of the tunnel, because every additional 10 centimeters in the diameter makes the cost of the project, the cost of the tunnel is much, much higher. And then there is a problem. So they're very, very careful, and they didn't want to make this tunnel too wide, only 10.8 meters. That's all. But again, we can discuss pros and cons by making cost-benefit analysis. But unfortunately, designer didn't want to start this cost-benefit analysis, and this was a problem. Nowadays, the tunnel boring machines became very popular in Israel, but more than 10 years passed after I gave the expertise, and unfortunately I failed. I was like a Don Quixote fighting with the mills. But now the time is different, time changing. So tunnel boring machines became very popular. Maybe Carmen and other people remember the RILEM conference and RILEM week in Hong Kong. It was, I think, in 2012, if I'm not wrong. And then there was an interesting tour inside the tunnel. And then we saw different machines. During this time, during this year, 4 different tunnel boring machines worked at the same time in Hong Kong. And Hong Kong is a not big country, it's like a city. And then what we learned, there was a machine which can adapt itself to extracting different quality and different mechanical properties, different rock with completely different mechanical properties, from the very hard to very soft and fractionated. So it's not a problem to find an instrument. And this is a paradox. Most of the excavated rock and construction earthworks is disposed, simply wasted. And the results are here: low stone extraction efficiency, irreparable economical losses, and environmental loss and damage. Technologies in building stone sectors are classified by me as follows: resources consuming and low tech, I can call them low tech, and resources saving and high tech. We speak about finished products, so-called dimension stone, and then we see different let's say quality, high quality, and all these characteristics are listed here. Consumption of quartz and sand and concrete production is huge, very high. So in 1 cubic meter of concrete, we need hundreds of kilograms of aggregates. 60 to 80 and sometimes even more % of aggregates is used in concrete. And then the consumption here is very low, if at all. So sand from carbonate rock can be used, recycled and sent to the aggregate production for concrete. So this is irreversible and sometimes catastrophic damage. And this is simply environmental friendly. So I'm thinking about possible environmental damage. Consumption of water energy resources. Here we have high, here we have low. Durability of the main product. Dozens of years. We spoke about service life of 50 years, or in some very, very important projects, we are speaking about 100 years. But here we are speaking about very, very long service life. For example, the stone products are very durable. In principle, building stone is the best building material created by nature. So just please don't explode, don't make a damage. Of course, we need to find a way how to find the deposits of the rock which is suitable for production of very qualitative, very nice products from the view of architects and the user. And this is not easy. We need to do much more testing, we need to do much more geological servers and find suitable deposits, excluding big cracks, of course. Environmental comfort in living spaces, satisfactory, and this is simply good. So dimension stone products can breathe and also are self-adapting to the environment. Consumption of labor is high here, low. Work motivation high, and unfortunately low. And then again we are classifying this technology on two big groups: existing, most popular technologies in the top, and in the bottom you can see the proposed technologies, both of them starting with hard rock extraction. Okay, then here we have construction object. We need to produce aggregates. We have as a product, as a byproduct of the rock, is a waste, which most of it goes directly to disposal, and fractionated material of unfortunately non-controlled quality. And here, in contrast to what you can see in the top, we are speaking about construction object, then dimension stone, as of course we have some so-called waste, but this waste is nice. We can control the quality. We can separate between different fractions of the same sand. We can make dust almost zero. Here we have a lot of dust pollution. Here we have nothing. It goes directly to the building market, like dimension stone. And a few words about the cost of the product. I don't know the situation about the cost of one, let's say, cubic meter of concrete in Mexico, in some other countries, Latin America. Let's say we have here in Israel, let's say $100 something for producing cement, and a little bit more for producing concrete as a material. But you need to produce aggregate, and aggregate itself for producing concrete doesn't cost anything, almost anything. I can tell you the prices which are public in Israel and maybe in many other countries are just a few dollars per ton. Aggregates are sold by tons, not by cubic meters, not by square meters, because this is not finished product. It's a semi-product. We need to produce concrete, which is our finished product. But aggregates is just one step forward. And this material costs almost nothing, $5, $10. If we wash aggregate, for example, sand, it can add $1, maybe more. But what about dimension stone? If you open the menu and price list of dimension stone products, for example, slabs and tiles, they are sold by square meters and cubic meters if we speak about big blocks, but mainly for construction, square meters. How much can 1 square meter of slab or tile cost? Let's say we have $50 or $100 for much nicer product, marble and dolomite, for example. And then the question, how many square meters we can produce from 1 cubic meter? And then it's very easy to calculate. The translation is very, very easy. For example, we can come to the conclusion, then 1 cubic meter of very good dimension stone, cubic meter, can cost, let's say, hundreds of dollars. and even thousands of dollars. And then if you compare with the price of oil, so it's much more than the price of 1 barrel, or one, not barrel, but cubic meter includes 6 barrels of oil. How much is 1 barrel now? About 100 or 60, $80. Multiply by 6, you can find the price of oil by tons. And then it's very easy to translate tons and cubic meters. So we just do not understand, do not imagine that we drop on the very expensive material, which is mainly produced, extracted for producing aggregates. So it's a very pity. Now, let me switch to another dilemma. I was very active several years ago and published some papers about gypsum versus Portland cement. Gypsum, as we know, has many advantages of early hardening and fine finish, but limited to internal use because of its sensitivity in water. Portland cement, in contrast, is strong in hardened state and durable in most conditions, but does not possess early hardening or the fine finish needed for precast components. About energy embodied. Total amount of energy used to manufacture a given material and then to transport is to point of use stage is very important. This is a critical measure of sustainability. By this measure, gypsum and gypsum products are one of the best and have a priority before similar materials and products made of PC. Maybe you know that for production of gypsum binders and gypsum products, we don't consume so much energy like we are consuming during the production of cement. Waterproof gypsum products. I published several papers about waterproof gypsum, but it's not easy. So in principle, we know how to make gypsum products waterproof. It's not easy, but we can do it. Then we can lower environmental loads caused by CO2 emissions by introducing more gypsum, but special gypsum. We can decrease transportation expenses, accelerate construction speed. The idea is not mine. The idea to overcome the disadvantages of gypsum, because gypsum is not durable in moist environment, by adding Portland cement, again, it was not mine, but if we add some active mineral additives, like pozzolanic materials, belongs to the Russian authors. Again, when most of European part of Russia was completely destroyed during the Second World War, and then they started to introduce gypsum products also for construction of external structures. And then some papers were published. I'm utilizing my knowledge of Russian. I met personally with Professor Feronskaya. Unfortunately, she died a few years ago. Professor Volzhinsky and Feronskaya published very good books in this year. So I tried to introduce these ideas, and we published together with Professor Bentor, one of my seniors in the Technion, and some other colleagues, papers. And we tried to add some active mineral additives like silica fume to make a peace between this antagonistic material gypsum and Portland cement to avoid the formation of calcium sulfoaluminate hydrates, which result in expansion and deterioration. Then you can see we just mix gypsum and cement. This is 75% of gypsum and 25% of Portland cement. In 2 days of water immersion, you can see huge expansion. The material loses completely the strength, cracked. And this is, of course, out of the way to implementation. And then this cube, which was immersed in water, was made of gypsum 75%, Portland cement 20%, and only 5% of microsilica. And then please look, the cubes are very strong, they're completely intact, they're very good. So you can see the graphs. We published these graphs in some of the papers. This is a capillary water absorption, huge in gypsum cement, 75 to 25% gypsum to cement. And this is the green curve, gypsum cement natural puzzolana. Gypsum cement microsilica, very close to what we have with gypsum cement natural puzzolana. So you can see this is competing with cement by capillary water absorption. And finally, the third dilemma about the low or so-called low contaminant construction materials. I'm speaking mainly about recycling and construction of the following byproducts of industries. These products are often contaminated, not only by chemical contaminants, but also, and this is a very serious problem, by radioactive contaminants, like phosphogypsum, blast furnace slag, coal fly ash, and other types of ash. You understand perhaps why ash? Because when you fire the material, for example, the rock or coal is a mineral which is extracted from the earth. Most of the material is lost because we produce energy, we produce vapor, we produce steam, and then we produce, let's say, from this coal, something which is not mineral, which is organic matter. Organic matter is completely fired, is lost. And then what we have in the end, we have unorganic matter. This is our ash. And of course, if we have, I speak about coal fly ash, 90% of material is lost, which is organic matter in the coal, and 10% only is left as ash. In this 10%, we have so-called enrichment of all unorganic matter, like metals, heavy metals, and radioactive metals. Fly ash, for example, it starts from the coal. You see, coal is a normal material which has normal uranium concentration. Here is ppm. And then in fly ash, it's a data from US coals. It's approximately 1 order of magnitude richer than coal. And then sometimes it exceeds the normative. Many years ago, unfortunately, the chimneys and other combustion installations of thermal power plants were not equipped with good filters. Now the situation is much, much better. But a few years ago, the situation was simply awful. So, and this was a prediction of the pollution, by the way, into the atmosphere by these different radionuclides. Look at the typical concentration of radionuclides in most common building materials, which may include byproducts. Here is the list of the 3 types of byproducts: by phosphogypsum, by blast furnace slag, and coal fly ash. You can see so-called radium equivalent. You can compare the numbers. Concrete, just concrete, it's much less. I can tell you that in the country like Israel, and we are rich with sedimentary rocks, which are dolomite and limestone, it's much, much less. We are speaking about 50 or maximum 100 becquerel per kilogram. Becquerel per kilogram is an activity, is called, is a unit of radiation. And this is not typical for many countries like Israel. We have much less. And here we sometimes have much higher. For example, in our country, the phosphogypsum has much more in Morocco. And maybe you know that Moroccans produce phosphogypsum and phosphate rock much more than most of other countries. 60% of phosphates are produced from Morocco. And then they are much higher by radioactivity, both phosphate rock and phosphogypsum. And this is a so-called high volume fly ash concrete. It's a typical composition of high volume fly ash concrete. You can see the content. You can see radium equivalent. It's our data for fly ash, which is richer. Cement is a little bit richer than aggregates. But totally, we have total activity of 1 cubic meter, not one, yes, 147, let's say almost 150. And a few years ago, European guidelines spoke about 150 for the materials used in bulk amounts. If the thickness is limited, for example, superficial, or other materials with restricted use, like tiles, boards, etc. So we have, according to this document, EU guidelines 112, much more liberal normative. But again, we are speaking about the same 150. Now the normative has been changed. The norms in Europe are more liberal than it was discussed and suggested a few years ago in this document. But again, we can be very close to the limit. I don't want to speak about the pluses and benefits of fly ash, which is very important consumable. This is very important resource for our and next generations. CO2 reduction, energy demand reduction, byproduct utilization are very important benefits of environment. And economical benefits, it's cheaper than cement. In principle, this is a byproduct. So what we have in the cost analysis, only transportation, maybe, and some more accompanying costs, but the material itself, it's just a byproduct. Radiological considerations. I published personally a few papers discussing radiological considerations of using cold fly ash in concrete. Yes, we know that gamma radiation, which is a direct result of the content of anorganic matter, including radioactive metals, is much higher. It can be 10 times higher than in many other mineral materials. But radon emanation power is low. Maybe you heard about uranium chain, and radon is one of the products of the disintegration of uranium-238, immediately standing after the precursor of radium-226. And then radon is very important contaminant for the indoor air. By the way, maybe you know that most of the radiation dose from natural sources is coming from radon, indoor radon. And very fortunately, radon emanation, so the amount of radon exhaling and emanating from building products is very low. Why? Because cold fly ash is just a very dense particles made of glassy phase, produced under very high temperatures in thermal plants. And there is very difficult for radon to escape this glassy phase into surrounding. And then this is the final part of my presentation. It's more philosophical. It's so-called ALARA. ALARA is a very important abbreviation in the radiological protection. This is very important for regulators and the people working in standardization committees. I'm also a member, a national delegate in ISO standardization committee dealing with revision of the standards dealing with radiation, natural radiation. ALARA is as low as reasonably achievable. ALARA is based on the graph, in the linear graph between the mortality and those amount of energy absorbed by the body. And the question is, And this is a real challenge to answer the question, what is really reasonably achievable? And almost nobody knows how to answer this question. What is reasonably achievable? Yes, as low we understand. We need to have zero, but every material extracted from the earth has some content of uranium, thorium, and potassium-40, natural radionuclides. These radionuclides appeared when the earth was created. It was more than 4.5 billion years ago. So they were first elements in the earth. So we cannot avoid of having some minor amounts of these elements in building materials. But what is really reasonably achievable? Risk of death. In one of the papers we published, we tried to calculate it by basing on risk of death. Then we using these numbers. I don't want to overload you with the calculation, but this graph we used for the calculation is based on the dependence between risk of untimely death and annual income, $1 per person. Now the income is much higher, but the paper was published many years ago, so it was not updated. And then you can compare the income in different countries in $1 per person. And then as a result, we can calculate how much would be to prevent exposure to 1 millisievert. This is a dose in Israel, because it is equivalent to increase of personal income by 2%. So it's milliards or billions of dollars. So it's incredible amount. So for some other countries, I'd like to skip it because we are closing to the end of my presentation. And then the question is how to make this cost-benefit analysis. And then the results will be different for rich and poor countries. So we understand perfectly then rich countries pay more, poor countries, communities, individuals express less willingness to pay to avoid environmental harms because have fewer resources. And then cost-benefit analysis justifies imposing great environmental burdens on poor countries. Very unfortunately, but this is a fact. We need to think about it. And of course, we need to compare countries with similar conditions, with a similar GNP per capita ratio. And very important to take into account objectivity and transparency for this cost-benefit analysis. If we fail to produce objectivity and transparency, we fail to convince the people. It's very difficult for the public to understand, participate in the products. So, and then very important issue is about information, informational regulation. In my opinion, this is a solution. It requires disclosures to the public because in many countries, the public is very afraid. They're scared about listening about radiation. But radiation is surrounding us. This is a part of the nature. We understand well that every building material contains a certain amount of contaminants, both chemical and radioactive. So we need to take into account the calculation, cost-benefit analysis. And then we need to calculate the risks, okay? And then we are speaking about a right to know. Right to know regime allows citizens and consumers not only to know about the risks they face, but also empower them to do something about those risks. Radon mitigation is one of the instruments. Introducing special additives into concrete mix to reduce radon emanation. We have some papers published which demonstrate usefulness of introducing silica fume and some other additives, reducing radon emanation. By the way, we have excellent example of labels, ecological labels of low contaminant product. and it's very popular in the Nordic countries, in Scandinavian countries. It's called Sven label. You see, so why not to speak about this instrument in regulation? And this is the final slide of my presentation, and conclusions are very simple. The question, and this is not an answer, this is a question to all of us, to our generation, to the next generations. How to find the common language between the parties of this triangle? Producer, yes, we need to speak about the benefit for producer, because they produce products and they want to make money. And the consumer, who are the consumers? We are the consumers, all of us. And of course the government, because the government is environmental authorities. First of all, environmental authorities and Ministry of Economics. All of these bodies are very important. They can restrict, they can manipulate in taxes, they can regulate the industry, import and export. They are very important, and when we need to find a common language with all of them. For example, environment is very simple. You cannot come to the shop and ask, please sell me 1 cubic meter of fresh air, because fresh air belongs to all the population, to all of us. You cannot ask, please sell us pure water or pure minerals, because the deposits, mineral deposits, belong to all of the country. And the governmental authority is responsible for this. So, and then this is just a question. If somebody wants to hear about the part 2, when I can go into more detail about low contaminant construction, and with a focus on materials made of industrial byproducts, going into details, we suggested a few interesting technologies for producing sustainable materials. And then I suggest to Pedro to discuss it in the next year, maybe in November or maybe before. We can find the framework if Pedro and your colleagues have an interest. Thank you very much again from Haifa. And this is again nice view from the Mount of Carmel, which is a biblical mount with a nice view on the Haifa Bay. Thank you very much. So I'm stopping the share and I'm ready for the questions.
Thank you, Costa. Thank you very much for the beautiful presentation. We have a space for a few questions. If you have some questions there. Enyo is arriving.
I see some questions in the chat. For example, last questions from Carmen, I think. Right? Very good presentation.
Yes.
On aggregates and on radioactive. Yes. This is the third part of my presentation related to some contaminants. By the way, I didn't speak about chemical contaminants. This can be included in the part 2 of my presentation. But chemical contaminants are also very important. For example, the same phosphogypsum. You have phosphogypsum in Mexico, by the way. And this phosphogypsum contains both chemical, like fluorides, which is extremely toxic, and some other acidic components based on P2O5, and then radioactive. So we need to take care of both of them. One question, if you know which is the dose of radioactive granitic rock. Yes, I know. But again, granitic rock is used for production of countertops, which is very popular for interior structures and some interior. But again, the thickness of these elements is not very high. And when we speak in the units of becquerel per kilogram, we need to take into account the total mass of radioactive elements in the building. And then if you take into account the thickness of the product and the surfaces, how many surfaces are coated by the same granitic rock elements, you come to conclusion that this material is not very much contributing, you see. So most of the focus should be made on bulk amounts. Granite and the tiles, by the way, ceramic tiles, we compared in one of the papers the radiation coming from, I don't want to blame Italian tiles, but we had an example coming from Italy and we compared with tiles produced in Israel. And Italian tiles, in our example, were very, very high radioactivity. But again, the thickness is only maybe 8 millimeters only. And then more questions. I'm going through. Some of the questions are written in Spanish, and then I need the help of Ana or Pedro.
We have some space. Victor Manuel Hernandez wants to speak or to say something.
Well, while Victor is arriving, Costa, really very interesting, and I was always fascinated by your work on this, on the radioactivity of construction materials, and why you think that this is not very much present in the congresses, because there are very few people and you are almost unique in this area. It is because the producers don't like to talk about, or because it's not very much known?
Carmen, thank you very much for your question. It's very good question, and I'm happy to answer. But this is my personal view. I started this activity because of the trigger, and the trigger was, in my opinion, please don't cite me. I know that it's recorded, but I'm sure that nobody from our Ministry of Environmental Protection is present, and then I can criticize them. They announced in 2008 coal fly ash is radioactive waste. Look at the definition. By announcing this material, which is a good resource, now we have many examples of the trade. For example, the trade between Portugal and Spain and some other countries, because coal fly ash should be utilized. Yes, I know in many countries, the regulators want to eliminate producing energy from coal, but coal is still alive. For example, in Poland and many other countries, is still alive. You should not you cannot forbid completely the production of energy from coal. You see, but what happened? Then our industry was in the big shock. They didn't want to listen about radiation, and then Ministry of Environmental Protection generated a standard, national standard, and about this, by this standard, most of concrete was very close to the border. And what is very close? If 10 or 20% or 30% is above, it can be a problem, because the court, if somebody among the consumers complains about validating, you see, the norm, it can be a problem. And then they didn't want to follow this standard. It was a big shock and a big scandal. And then I started to look into it. And then finally, we produced a standard. I was chairing the last committee. We revised the standard. Still, this is the most strict standard in the world. In some countries, in Europe, for example, the standards are stricter. For example, in Denmark, in Italy, then the European regulation, UBSS, Basic Safety Standards. But again, the people which are familiar with this issue, they know what I'm speaking about, but the producer don't want to hear about it. Again, just an example. In Europe, we have, and in some other countries, we have a standards regulating radioactivity of building materials. In the United States, I don't know the situation in Mexico, in some other Latin American countries, but in the United States, they don't have any standard regulating radioactivity of building materials. But on the other hand, they have much stricter standard regulating indoor air. And then if you summarize the dose coming from gamma, which is proportional to the content of radionuclides, like radium, thorium, and potassium-40, and radon, if you summarize from the viewpoint of consumers, it does matter what will be the result, what will be the mortality, because you need to take into account both the components of the radiation dose. And the Americans are very strict, much stricter than Europeans and any countries in regulating indoor radon. My elder son lives more than 18 years in America. And I know the situation very well. You cannot sell your house. You cannot buy your house without testing on radon. This is penetrated into the brain of the consumers, everybody. But look at the position of the industry. The industry doesn't want to regulate. They are making a lobbying. I don't want to blame all the industry in the United States, but I can understand the underwater, let's say, considerations. So perhaps these considerations are also popular in some other countries. The industry doesn't want to hear about this problem.
Yeah. Pedro, is Victor already asking? Pedro? Well, Costa, I think that this is an important subject because, for instance, with the geopolymers, it looks that they say that it's more ecological, but the amount of fly ash by cubic meter is much higher. In that case, I have appreciated very much your presentation because you are balancing. You are just making in the total evaluation more components that have not been taken into account. In that case, we look forward for your presentation next year.
Okay, great. It will be a pleasure to explain these things in the second part. This is very controversial, of course, and of course, I'm also criticizing the existing European norms because they are based on so-called specific radioactivity measured in becquerel per kilogram. And this is not representing the real contribution of the building products in the total building, in the square meter of the dwelling. You see, so this is a very important issue. We want to improve the regulation, but it's not easy. It's not easy, like you know.
Yeah, Pedro is telling me that they had a problem with internet, and Enio, it looks that you and me could close the seminar because I don't see that there are more questions there. I think that Pedro had, but I have not found more in the chat.
Okay.
I was opening Enio because I know that you are in giving classes and you couldn't arrive.
Okay, thank you very much, Professor Carmen Andrade. Yes, I can say some words to finish this conference. first, in the name of the Latin American Association of Quality Control, Pathology and Construction Recovery, we would like to thank Dr. Konstantin. Thank you very much for this excellent presentation. We appreciate very much the opportunity that hosting gives us to participate in this amazing conference. Thank you very much. Thank you, Julio Medina, that is here. I would like to thank Professor Mari Carmen, Dr. Pedro Castro for the initiating this conference and for the essential contacts of Dr. Konstantin for this moment possible. Thank you very much. And I would like to thank the audience who are watching this senior webinar. And I hope see you in the next senior webinar. Thank you very much.
Thank you very much, Mr. Pazzini. It's my pleasure. And I believe you understand Italian. It's piacere.
Piacere. It's a piacere.
Yeah, it's my pleasure.
Thank you.
Pedro, que ya has vuelto de... Si tienes alguna pregunta, porque Víctor quería preguntar algo, si tienes alguna pregunta, si no ya tú y Julio termináis.
De hecho, el protocolo, Pedro,
solamente agradecer a Costa, de nuevo, ¿verdad? Me desconecté, me perdí, se me fue el internet, entonces vine corriendo aquí donde Alexia para poder cerrar. Y bueno, Costa amablemente nos ha ofrecido la segunda parte de esto que escuché Genio está comentando. Entonces, con mucho gusto, el próximo año estaremos en ello.
Bien, y pues nada, agradecer a todos los que se conectaron también el día de hoy. Gracias, doctor Consta, por la presentación. Y pues al compas, muchísimas gracias.
My best wishes, Costa. My best wishes also for your wife.
The same. Thank you very much,
Thank you
Dr.
very much.
Konstantin.
Yeah.